voltage. Okay. Hello again for everyone that is joining us in a Zoom meeting and you guys that are here. I hope you are had a great day so far. And let's start today's session. Before we start the concept, is there any specific question that you want to ask or like you want us to discuss? No? Okay. In previous session that we had, we talked about the grid following inverters. And basically, we said, okay, we have a category for inverters named grid following. They are type of inverters that they have to follow the grid. So they need a grid in order to tune their own parameters, and they always following the change on the terminals, on their output terminals connected to the grid. That being said, we said, okay, the most important part that would help us to have a grid following, a stable grid following uh, inverters is how we implement the control system into that inverters. We talk about the PLL, we talk about the PID control system. We said PLL tries to control to synchronize the inverters with the grid and make sure that we don't have deviation over the frequency, and PID control tries to answer the demands of the grid. So if there is a voltage change or a current change, meaning there's a load change, we could address that, and basically our inverter could supply that demand from the grid. Are we clear so far? Now, today we are going to go a little bit deeper into the PID controller. Okay, as we talked about that in previous session, we are going to talk about specifically PID controller and how we could implement the PID if the PowerPoint works with me. Okay. We talked about how PID works in previous session, but in order to refresh our mind, basically the problem definition in PID control relates on three objectives. Okay, one is key process of the variable for the control. So we have to define what variable we are trying to control. Okay. Next step is we have to try to define the errors that we have at current time. So we had a set point, our destination, and we had a current value, which is our basically where we are going to start. The difference between the two are going to create our error signal, the gap that controller had to fill or push the variables to cancel out that gap, and we call that error signal. In inverters, mostly as we talked about, we had active power control, reactive power control, frequency control as our primary controls, and current control as a secondary control. We said the current control is basically a protection, it has a protection application rather than the actual control. So what actually answers to demand at the terminals is active power and reactive power control. Okay, and we said we are going to talk about that in detail after the midterm, but in order for you to have an idea, when we want to control active control, we said we have to control the phase of the voltage. By controlling the phase of the voltage, we could control the injection or consumption of active power, sorry, okay? And for reactive power control, we mentioned in previous session that if we wanted to control the generation or consumption of that reactive power control, we control the amplitude of the voltage. Okay, so our voltage is AC, it's a vector, it has amplitude and phase. Phase would decide how much active power you inject. Amplitude would decide how much reactive power you inject or consume. Okay, so that being said, basically all control variables would shrink to two variables. We have to control our voltage, okay, for active and reactive power. And for that PLL thing, for the synchronization, we have to control our frequency. So in inverter-based resources, we have two main variables to control in our control system. Are we good so far? So we have to define the error signal for these two variables. And as you can see in the screen, it's pretty simple. The error is basically the difference between the set point and the current value, or like the output value that we have, okay? For each of them. The objective of the control is to eliminate that error. So it would push our current value toward our desired value. Okay, so this is the third key aspect of a PID controller. Now, any questions so far? No? Okay, yeah, go.
About those two reactive power, safe or power phase.
Yeah.
So, what do you mean by the phase? Is it the difference between the phase of the generated voltage by PSC, but the difference between phase of the voltage of the PSC and the AC side?
You have the IBR voltage, the sinusoid, the not pure sinusoidal, the PWM, sinusoidal PWM voltage that you create at the output of your full bridge or multi-level. Okay, we call it VIBR. It's a vector. It has an amplitude and it has a theta. Okay, I call it theta IBR. Now, at the terminal, after the filter and all the stuff that you had, okay, at the terminal that is connected to the grid, your point of connection to the grid, okay, we have, let's call it V of point of connection, okay, to the grid. We have another voltage that is the voltage kind of like defined based on the grid situation, okay? So that voltage also have a theta, an amplitude, and a theta POC. Okay, now the difference between theta POC and theta IBR, the two phases, okay, at a time. This is a time function. So frequency also defines that theta too. Okay, so this is omega t plus theta naught. Okay, so it's not, do not consider that as a phase as a constant number. Okay, it's varying through the time. So the difference between the two theta would define how much power you inject or consume, okay, through your connection. And the difference between these two amplitude would define how much you have reactive power to inject or consume. Like, for example, if the voltage of the IBR, the amplitude is lower than the amplitude of the point of connection, that means you are consuming reactive power from grid. Okay? And if we tune the voltage a little bit, or like whatever we want, whatever amount we want, higher than the voltage of the point of connection, basically we are injecting reactive power to our point of connection. Same goes for the thetas about the active power. When we want to discuss the power flow, okay, in after the midterm, one of the weeks that you are going to have, we are discussing the power flow analysis. Okay, on the power flow analysis, when I introduce the power flow formulas for active power and reactive power, you would see what I mean by the effect of the thetas on active power and the effect of the amplitude on reactive power. It comes from the power flow analysis. Did I answer your question?
Yeah, practically, how do you define the reference active reactive power?
What do you mean reference?
Because if we are controlling those two,
Mhm.
there must be some
Exactly.
the base that we used to compare. So how do we define that?
Yeah. For control system in active and reactive power, okay, as we defined our error signal, okay? Our destination, basically our purpose, the inverter's purpose is to supply the loads on the terminal that is connected to the grid. Is that okay? Okay, that's our purpose. We added an inverter to supply some load. Okay, now on the terminal of the grid, when we read the voltage, amplitude, and phase, is basically we are reading how much load the grid needs us to provide. So what we read at the terminal of the connection, the POC, that need is our destination. That defines our set point. Okay, and the current value, the current situation that we have at our inverters is our V out, or our current method that we have to like push it toward that set point that grid demands. It basically is the reason that we say is grid following. One of the reasons is that aspect, because it has to follow whatever grid demands. Are we good? Did I answer the question? Any other question about the general PID? No? Okay. Now, when we define the situation, the parameters, and the error signal, the way that PID control works is the continuous correction of the error. Okay, we measure PID controller. We are gonna see how PID controller tries to like eliminate the error. Okay, calculated the error and tries to like send the actuation signal to eliminate the error. And that actuation signal would affect the PWM situation that we have. Okay, so we could address that error. Is that clear? So we measure the current situation. We calculate what we have to do to go toward the set point or desired point. We calculate the changes that we have to make, and we send that to PWM to change those parameters. So PWM would create output closer to our desired point. Is that clear? So this is the kind of like the loop of PID control, and it's continuous. It's not like a single time kind of loop. It's a continuous time that is always working. Okay, it's always rotating through this loop for both voltage and frequency. Okay, now to be more precise on the kind of like the analogy of and the design of the PID controller, okay, the PID formula, okay, defines the PID controller based on the name. You could kind of like imagine what we are talking about. First, the PID controller stands for proportional integral differential. Okay, so it would have three terms in order to process the error signal that we calculated. Are we good? So we have an error signal. PID processes that error signal to create new output. Okay, actuating kind of a signal. Now we have three terms. One term is proportional. Based on the name, it means it's simply read the error, apply a gain, and we have our proportional portion of our control signal. The first step. Okay, let me show in the so people in the Zoom meeting could see it also. Okay, we calculate the error, we add a gain, we have our proportional portion of our control signal. The integral part would process the error signal further, calculate an integral of the error signal from the time zero when you push start on your inverters, okay, until the current time. So it's always adding accumulating all the errors, okay. Apply a coefficient or a gain, and it creates the integral portion of our control signal. Okay, I am gonna tell you what is the intuition behind that, why we need proportional y, we need integral what they do. Okay, in the later slide, the future slide, I'm going to give you the intuition of those aspects. The third part is the derivative part. Again, it's a processing kind of like situation. It would calculate the derivative of the error signal, because we said error signal is a time variant function, okay, change with time. It would calculate the error, the differential, the derivative of the first derivative of the error, add again, and we have the third portion of our PID control signal. We add these three, okay, to create the correction signal. So as you can see here in the graph, we had our set point and we had our output. Here, we calculated the error. We feed the error to the three-part, proportional, integral, and differential. And then we add them to create the control signal, okay? And when we have our control signal, we inject that control signal into our process, which is the PWM that we have in inverters, okay? Because the control signal would define, like, for example, what is the modulation index of the PWM should be, how much we have to like shift the phase of our reference signal, you know, these kind of stuff. Or in PLL, how much we have to like change the frequency of our reference signal. Those values, those leverages that we have in PWM, we talk about that, what control leverages we had in PWM when we discussed the PWM and SPWM. Remember that? So this process is basically means we inject the control signal and apply it to those leverages. So now we have a new PWM situation that should be based on our process, should be closer to our set point. So next time that it would try to calculate the error should be smaller. Are we good? And it goes on and on and on until we get to the point that error is zero, which we are never gonna get to that point. But ideally, if we get to the point zero, that means all of these are gonna be zero. That means we don't have any correcting signal injected to our process, so process keep on going at the previous setting. Are we good? So this is how we could, basically the algorithm of the PID controller and the formula for the PID controller and how it works. Any question? No? Come on. Work with me. Okay, now let's
Congratulations, it's a bargain. Ollie's is celebrating the opening of its new store in Norman. Wednesday, February 26th
you have to wait
at
for
9 a.m.
the
Find us off Lindsay Street next to Dollar General, the old Smart Saver Grocery.
Come on.
You've never seen deals like this before.
Ollie's! Good stuff, cheap!
Where is the extra feature?
This video is brought to you by us, RealPars. Join the top 1% of PLC programmers. Learn from the world's best so you can
This
join their
video
rank.
is gonna
Head on over to
try to explain what I
realpars.com
explain in
and
different
start
languages, so
learning
it's
now.
gonna be more intuitive. I want to like hear
In
it
this
from
video, we're going to talk about the PID controller and its transformation from a single station device to what it has evolved into today. We're going to explain why PID controllers are used in industrial processes instead of simple on-off controllers. We'll illustrate how controller settings called proportional, integral, and derivative affect different processes under control. We'll also provide an overview of the very important activity called controller tuning. Let's start with a discussion about home temperature control, as it's familiar to lots of people. This house has a furnace that distributes heat throughout, and a wall-mounted controller called a thermostat. The thermostat has a sensor that measures the house temperature and compares that measurement to an adjustable set point. If the room temperature is below the set point, the furnace is turned on. When the room temperature increases above the set point, the furnace turns off. This type of control is referred to as on-off or bang-bang control. Here's a plot of what the room temperature does over a period of time as the furnace turns on and off. As you can see, the temperature is not exactly held at the set point of 70 degrees Fahrenheit, but cycles above and below the set point. On-off control may be okay for your house, but it is not okay for industrial processes or motion control.
Well, ever since he was a baby, they knew the kid was
Now it's
crazy by his head.
Let's look at an example of tank level control to explain why. The valve fills the tank as the pump drains it. If the valve is operated with on-off control, the water will fluctuate around the 50% set point. For our purpose, let's say the fluctuation is plus or minus 10%. In most industrial applications, this fluctuation around the set point is not acceptable. Okay, well, what if it's possible to throttle the valve and place it in any position between on and off? Now we can move on to talking about a PID controller. P stands for proportional, I stands for integral, and D stands for derivative. Because every process responds differently, the PID controller determines how much and how quickly correction is applied by using varying amounts of proportional, integral, and derivative action. Each block contributes a unique signal that is added together to create the controller output signal. Let's look at how a PID controller fits into a feedback control loop. The controller is responsible for ensuring that the process remains as close to the desired value as possible, regardless of various disruptions. The controller compares the transmitter process variable, or PV signal, and the set point. Based on that comparison, the controller produces an output signal to operate the final control element. This PID controller output is capable of operating the final control element over its entire 100% range. Most modern PID controllers are part of a PLC or DCS and are created in the program control logic using block commands.
Congratulations! It's a bargain! Ollie's is celebrating the opening of its new store in Norman, Wednesday, February
you ever
26th at
seen
9 a.m.
so much of it?
Before PLCs came along, a PID controller was a standalone device, responsible for controlling one loop. A control room would have dozens or hundreds of standalone controllers mounted on a panel. There are still many standalone PID controllers being manufactured and used today. Okay, let's get back and talk about what each of the P, I, and D components of the PID controller does. Remember earlier we said that the PID controller is responsible for ensuring that the process remains as close to the set point as possible, regardless of various disruptions. Let's refer to the difference between the process variable and the set point as the error signal. The proportional block creates an output signal proportional to the magnitude of the error signal. Unfortunately, the closer you get to the set point, the less it pushes. Eventually, the process just runs continuously close to the set point, but not quite there. That's when integral jumps in. The integral block creates an output proportional to the duration and magnitude of the error signal. The longer the error and the greater the amount, the larger the integral output. As long as an error exists, integral action will continue. The derivative block creates an output signal proportional to the rate of change of the error signal. The faster the error changes, the larger the derivative output. Derivative control looks ahead to see what the error will be in the future and contributes to the controller output accordingly. That brings us to a term called controller tuning.
Whatever you do it for less at Harbor Freight.
We said earlier that every process responds differently, and that the PID controller determines how much and how quickly correction is applied by adjusting proportional, integral, and derivative action. Controller tuning involves correctly setting the controller P, I, and D values for specific process requirements. Interestingly, the correct settings achieved by controller tuning can differ vastly between processes because of specific requirements. For example, after the controller has been tuned, a set point bump of 1% in a tank level control produces a quarter wave damped response. This type of response may be suitable in a tank-level process, but could be disastrous in a motion control process. There are many different manual methods for tuning a controller that involves observing the process response after inflicting controller set point changes. One method involves increasing the amount of set point change and repeating the procedure until the process enters a state of steady-state oscillation. This method of tuning produces adequate results, but is often impractical in many applications. For example, how practical is it to force the fluid level in a large tank to reach a steady-state oscillation? Most process controllers, PLC, and DCS loop controllers sold today have auto-tuning capability. The PID controller learns how the process responds to a change in set point and suggested PID settings. Regardless of whether the initial PID parameters are derived from the manual or auto-tuning methods, additional tweaking is often required by seasoned automation professionals to get the response desired. That should do it for this video. If you want to learn more about PID control, you might want to watch our other two videos called
Okay. Any question about the videos? So it's basically talked about the process of the PID control and what it means to have a PID control. Now, I wanted to give you a little bit more intuition about what is the proportion do, what is the, actually the video mentioned it a little bit, but I wanted to emphasize that. What is the integral do, what is the differential, okay? The proportional value, as you can see, has two parts. One part is the error itself, and another part is the gain. Actually, all of them has two parts, okay? The integral of the error and the gain, the derivative of the error and the gain for differential, okay? Now, what those mean, what they do, okay? In the proportional section, basically what the controllers do is to find out how much we have error, okay? And tries to eliminate directly the amount of error that we have and apply it to the output. For example, if we have a high error, like we have a very large value of the error, it would create a larger control action to change the values, okay? So we would get closer to our situation. Now, what is your guess about the problem of that proportional value? If we only use the P control, only use the P proportional, and we know that it directly acts on an error signal. So if we have a very high error, it would create a high value change in our setting. If we have a lower error, it would create a lower value of change in our setting. What is the problem if we eliminate the I and D and only use the proportional error controller? What are your guess? Do you have any idea of what is the problem for that? One of the problems was actually mentioned in the video.
Was it a situation where it just oscillates the exact same? It doesn't ever.
The oscillation would happen, okay, eventually, okay, because look at the formula. In the formula, we have KPET plus, I factorize the T bar. KI integral of E plus KD derivative of E. Okay? And it should be equal to something. Now, look at this. If you want to solve it on paper, the first thing that you do is to get rid of the integral because you don't want it to have integral and differential in the same equation. If you do that, what you end up is KD d square dt square of E with derivative once for all the parameters. plus Kp dE over dt plus Ki E. Second order differential equation. What is the main aspects of the second order systems? It has an oscillation. So oscillation would happen. You can eliminate that, damp that oscillation, okay? But you have overshoot and undershoot no matter what you do. But you can manage to like control that, okay? Are you working with the RLC circuit before, or did you work with RLC circuit before? Okay, so you've seen how you could damp the oscillation, or like you have a critical oscillation when oscillation would not get damped and it's always there, you know, something like that. So what the proportional do is, as we said, proportional, if we see a high amount of error, it would create a high amount of correction. Okay, that's fine. That's what we want. Okay, but let's say this is our set point. When the value get closer to the set point, now the error is small, correct? So the correction would become small. So basically it means you can consider that it never gets to the set point because it's like an exponential decay, okay? It would limit to the set point and would never get to the set point because as much as you get closer, the error never gets zero because proportion of the error would be added to the control signal. Are we good? So we are going to have an offset, or you could call it accumulated error that is always there. How we could deal with that? Then kicks in the integral part. The intuition of the integral is basically the definition of the integral is summing up the value through the time or any axis that you want to like define, any dimension. Okay, so what the integral do is calculate the accumulative error through the time. So if you have an offset, that I part would catch it and send a correction signal to eliminate. Are we good? So proportional part is basically trying to eliminate the majority of the error. The leftover are dealt by the integral part. Okay. Now, what is the effective of the derivative part? The derivative part calculates the change of the error through the time. So it would calculate how fast our error is changing. Okay. So what is the significance of knowing how fast the error is changing? What it Or let me ask another question, because I wanted to like give you an intuition about the integral and differential too. If integral give us the accumulated errors, meaning it kind of works as a memory, okay, and give us all the errors in past, and we know the differential is the reverse of the integral, what differential gonna do for us? It's predict. So integral calculate the errors in the past, the remaining errors, the residuals. Okay. The derivative part tries to predict the future by calculating the rate of change. Okay. So what is the significance of knowing what's gonna be happening in future? Why we need that? If we have an error signal that is changing super fast, oscillate super fast, okay, then this prediction would predict, okay, how fast it would go. So it would kind of like tries to control these overshoots and undershoots by predicting what's going to happen. Okay, so because P and I would try to eliminate that, but we know that they cannot just directly go to the set point. They're gonna like oscillate around the set point until we get to that. Okay, how much we deviate from set point in all of those overshoots and undershoots. Okay, how we could control them by predicting the change and try to damp them. So the derivative tries to smooth the process, lower overshoot and undershoot by predicting the future. Are we good? So this is how it works. Now, this is the error signal, the integral and the derivative. What is the K do for us? Because we are tuning those gains in order to get different type of like, different action from our control system. Let's focus on only proportional. Okay, we have an error. Okay, we wanted to like act on it. We don't have integral and differential now, only proportional. Okay, if K is 1, we don't have any gain. What the controller does, it simply calculates the difference and tries to cancel out that difference directly, okay, in our output. Are you good? What happens if I add a gain higher than 1 to that error? We have an error. Okay, this is our error. This is our control value, output of the PI. Okay, if I have error, like for example, 0.1, and I define the KP as 2, for example, what's going to happen? It is going to overshoot and undershoot because we don't have the differential yet. Okay, the differential is controlling the overshoot and undershoot. Okay, so as long as we don't have the derivative part, we have overshoot. Okay, now if I set the KP as 2, the controller would see the error, but would apply twice the error as the correction. Is that correct? No. This is my set point. I want to get to that. At time equal to 0, this is my error, correct? If I have 2, it would apply twice the error for time equal to 1 for here, correct? So it would push me here, correct? Now, at time 2, this is the error. It would push me here. And it's going on and on until we have a situation. Now, if I put a value lower than 1, like for example, I put a KP, this is our set point, KP equal to half, then what's going to happen? Then this is my error at time 0, correct? What is going to be the value for time 1? Half of this error, correct? So it gets here. Now, in time 2, my error is this one. What is going to happen? It goes here. And then it goes here and here. Oh. So can you see how it affects the output? So we would have, by controlling the KP, we would first of all control how significant the overshoot and undershoot could be. But most importantly, if we have a higher KP, okay, the algorithm reach to the set points faster than when we have a lower KP. Imagine if it's instead of half, I have 0.1. Then this graph that you see here become like this. So it takes longer time to get to the set point if we have a less gain in our proportion. Are we good? Now, for the integral, we said this is going to accumulate the steady state error, the residuals, okay, and try to eliminate them. Now, we have a residual. What is the significance of K?
After, like there's a smaller K, you'll get, I guess, more days.
Okay, let's look at the values. Okay, we said we have, let's say this is our residual and this is our set point. Okay, we have a residual. Okay, if I define the Ki as like 0.01, 1%. Okay, how much effect the I part, the integral part, would have in the overall control signal at the output? Not very much. Okay, so it would eliminate a little bit of the error. So it needs more time to 1% by 1% eliminate that offset. Is that now clear? Yeah. So that Ki would also show you how fast you can or how effective you can eliminate your residuals of the error, accumulated error. Same goes for the derivative part. Okay, if you look at the KD, okay, it sees the change. If I have a lower KD, basically means I try to I see there is a speed of change, the rate of change for my error. Okay, if I apply a lower gain, that means I'm trying to damp the prediction effect, the effect of the prediction part into the control system. Meaning we have a less correction on the overshoot and undershoot. Are we good? Is that any question about that? Now, practically, when you wanted to tune that, normally if you don't want to auto tune, you would not manually tune, what they do normally is for all three gains, they start small and they try to find the optimal value by increasing the gains gradually. Okay, so because if you start big, then you have a lot of undershoot and overshoot, and it's, your system might get unstable. Okay, or pass a certain threshold of the withstand. Are we good? So this is the practical tip. Yeah, go.
Are the gains for each PID, are those independent of each other, or are those the same value?
No, independent. When we talk about the PLC or those controllers, that the standalone controllers, they are basically digital electronic system. Okay, so you actually set the values, so they are independent. If you wanted to drive the analog system controller, we already talked about that. It's a second order differential equation. So it's RLC circuit. Okay. What was the RLC circuit solution? We had two routes for the RLC circuit solution. It's second order. So we have two routes if you wanted to solve it in a Laplace transform. You remember Is that familiar? Are you familiar with that? I'm going to explain that. Okay. Let me find a place to write down. So the derivative that we had, if we do the Laplace transform, it become KDS2 plus KPS plus KI equal to 0. This is the Laplace transform of that second order differential equation that we see in the previous slide. We replace each derivative with S, with one S. Okay, now this is the second order, like a parabolic algebraic equation. So it would have, this is kind of like the situation. It's the second order. Okay, it would have two root. Correct? So when you want to like calculate the two roots based on the values of KD, KP, and KI, which basically in RLC system, if I don't forget, let me drive that. This is gonna be RI plus 1 over L integral of 1 over C integral of I dt plus 1 plus L di dt, correct? So KD is L, this is KD, this is KI, and this is the R is KP in the RLC circuit. Okay, now that value, if you run the values for the roots, S1 and S2 are gonna be alpha plus minus square root of alpha plus omega minus omega square. No, sorry. A square. Okay. The alpha is called Neper frequency. The omega is natural frequency. Omega is 1 over a square root of LC. Okay. Alpha, if you run the equation, you would see that. This is if you I want to just give you the answer. It's 1 over R2 RC. Okay, so now that when you see that, if you wanted to like do the analog signal, now you see that the KD, KP, and KC is basically creating the values for your results, for your how much overshoot you have, how much undershoot you have. Is that clear what I'm talking about? So it's not like you have one value that defines everything. They are interacting with each other. Are we good? Did I answer your question?
Yeah.
Okay. Any other question? No? Okay. Now, this is a practical example. I want to like move a little bit faster. So it's basically the same situation. For this example, we have the voltage control. We try to define the error signal. Okay. The proportional term increase for like in inverters, increase the duty cycle or decrease the duty cycle based on if you wanted to like add a voltage or lower the voltage. Okay. The integral part tries to eliminate the steady state error. Okay. And the derivative part tries to control the overshoots. So you wanted to like have voltage control. It would affect your duty cycle in your inverters. Okay. Are we good? How we could affect the duty cycle in the inverters? What was we have two leverage to do that. Do you remember that? With what parameter we can control how much the switch is on and how much is off?
High time look, but the frequency, which means
Which frequency?
That you sample your,
The switching frequency.
yeah,
That triangular frequency. You have one leverage on the triangular frequency. You could control the how much on and off should be. Now, normally they don't use the switching frequency. They use another value to control how much the switches should be turned on and off. Modulation index. By lowering the value of the reference signal, okay, you basically lowering the time when the switches are on or off. Because switches are on when the reference is bigger than the carrier. If the reference is going to be lower, then there is a lower time when the reference is bigger than the carrier. Do you get what I'm saying? So this is how we play with the modulation index, okay, by applying the control signal and getting whatever we want at the output. Same goes for the frequency. We adjust the PWM period here for the frequency. We calculate the error signal. This is what's going to happen in PLL, which we are going to discuss next session, okay, deeply, okay, because it's important. What is the change, what we should change in the PWM if we wanted to like adjust the frequency at our output? We had two signals. One was the reference signal, another one was the triangular signal carrier. If we want to have like a 60 hertz frequency at the output, how we could force this PWM for such a frequency at the output? The reference signal. Yeah. So the frequency of the reference signal defines the frequency of the output. So you wanted to like control the frequency, tune the frequency, eliminate the error, whatever you want to call it. You change the frequency of oscillation in your reference frequency. Are we good? The reason that they don't use, that's a good point. The reason that they don't use the switching frequency for duty cycle control is because it's easier. For voltage, you control the amplitude. For frequency, you control frequency. So you have only one signal to play with. You know, simpler control circuit. And you keep this solid. Make sense? Any question? Now, we said one of the ways that we could like tune our controller, meaning define or like design that KP, KD, and KI in our controller is manual. Like start with a small signal and see what's going to happen. Okay. It's not very accurate way or like sophisticated way, but actually like it's used a lot in less sensitive kind of like situation, not robotic. At that like heat situation or like you know the water tank situation that in the video you see. Okay, that doesn't kind of like make any difference to manually tune or like auto tune. Okay, now for tuning goals, what are the goals of tuning? We want quick response, okay, minimal overshoot, no steady state. Are we good? For quick response, we know what to play with, that KD, sorry, KP. For minimal overshoot, what was the value? KD. KD controls the overshoot. For deleting the residuals or a steady state error, it was the integral drop. So we could control how effective we could be on that with KI. Okay. For tuning method, the trial error is the manual one. Let's see what's going to happen. And we change the values to get to the point that you want, but the kind of like the more accurate and better method is called Ziegler-Nicholas method. Okay, I add this video for how you could tune using the Ziegler-Nicholas method. It's a little bit long, so I'm not going to play it in the class, but I'm going to post this PowerPoint so you can like have the link to that and like watch the videos. Okay, it's very good on to see how you can auto tune your system. That being said, Ziegler-Nicholas method has a very good option, very good significant, and it's on initial tuning. So in manual tuning, you don't have initial value for KD, KP, KC. You just put randomly a number. Okay, Ziegler-Nicholas optimize. It tries to create an optimized value for the initial value and then adjust it with the autotune. Are we good? So this is one of the most kind of like significant application of the Ziegler-Nicholas, the initial value of the KP, KI, and KD. Are we good? No. I said no. Okay, now one thing that is kind of like the problem in anti-wind-up techniques, in the PID techniques, is the accumulated error in our memories. We had the integral. Okay, that integral always add the errors on top of the errors over and over. Okay, and you can see like if I start the PID, push the start on a PID today, a week from now, the portion of integral is gonna be a huge number because it didn't get rid of the previous data, it just add them together. You know, so how we could deal with that? How we could manage to not having a saturated or like, you know, a very kind of like huge portion of the residuals which are not accurate, okay, is just accumulating a bunch of error through the time, not the current value of the error, steady state error, okay? How we could deal with that? Then it came anti-wind-up techniques. Okay, we need to reset basically our integral once in a while. You could see how it acts. Like if you don't use the anti-wind-up, you could see that there is a lot of accumulating error on top of each other, they added to each other, okay? But if you reset that, you would eliminate the previous version and it's like starting from a new time zero. Now the accumulation that it calculates is more closely to the current situation rather than it be affected to the infinite time before that, you know? Are you good? Any question? Now, when you wanted to like design a PID controller, there's a step-by-step value. This is kind of like a summary of what we discussed. Okay, the step-by-step value of our that you have to do in order to design your PID controller. First, define the goals, as we did in I think second slide that we had. You have to define what variable I'm gonna control or calculate the error or, you know, actuate it, send an actuation signal to the control system. Okay. Next, you have to model your system. Your PID, okay, is a closed loop. It's a closed loop. This is your controller. This is the error. This is your PID. This is your system. And this is going to be your output, which is going to come back to the error. Okay? What that define this output, Y here, is not just the PID. It's also the system. So you have to know what is your system do. S domain is easier way to like analyze if you want to theoretically want to analyze that. Yeah. You can use just simulation, gonna be the same. Okay. But if you want to theoretically design your PID, best system is S domain. So you are gonna like run a KVL or KCL over your inverter. Okay. How it works. Input is the correction signal. Output is the output of the inverter. From that point, this is a one loop. That KVL KCL would gives you a differential integral equation, which would turn out to a certain order of the differential equation if you get rid of the integrals. Okay, and by Laplace transform, you know how to turn the differential equation to a Laplace equation. Now you have your system equation. Okay, now if you have your system, now in order to define what is Y, you have to have your feedback loop equivalent Laplace equation to know what's happened in input. So how we could create the output. Then we could like run the KVL. Okay, so you are not gonna need that here. I wanted to say like as this part is you need to like know the control system, Laplace theory control system, know how to drive the Bode diagram and what Ruth-Lucas and Nyquist, diagram on the control system is not within this course, okay? But this is how professionally you could define it. I'm gonna upload a paper that all these steps for a PID controller for an inverter, so you could see what I mean by modeling the inverter, what I mean by Bode diagram, pole zero kind of like analysis, and what is important because we want to like have a stable system. By analyzing the pole and zeros in our system, we could avoid going toward the poles, which is the denominator zeros, which makes in a stable situation. Is that clear for? I don't know how much you have information about the control system. Do you? No? Okay. That function has a certain S plus B, and for example, this is an example, and we have like S minus C in the denominator. Okay, you don't want to get to the point that S is equal to C because it makes the denominator zero, okay, which means the whole situation become infinity. That zeros of the denominator, we call it poles. Okay, they are the values that the system gets unstable. We want to avoid them. The zeros in a denominator, we call them zeros. They are when the system don't do anything. The output is going to be zero. Good point to like introduce the next course. I am going to teach intro to the control system in fall. I don't know how many of you are going to be here in fall, next fall, but I am going to talk in detail how to analyze the control system, all those aspects. Next fall in intro to control system is 4413, EC 4413 if you wanted to like, if you are interested. Now, so any question? When you define the model of your system and you find out, okay, where to not go for the instabilities and you know what's going on in your system, next step is to set up your values. Now you know what are the optimum KP, KD, and KIs. If it's digital, it's directly applied to the system. If it's analog, we said that KP and KD and KI is basically could be gained at specific values by tuning the R, L, and C in your analog signal. So you could translate those optimum value into the calibrated value for your circuit design. Is that clear? So next step, circuit design. Step 4, you have your PID control. Let's test it how it works because we have some errors in our calculation. It's not like if we have like an analog system, if we tune for an RLC, it's not like if you count for the R equal to 1.20, you don't have that in the market. You have to calibrate those numbers. So you have to change that. There is going to be an uncertainty on the performance of what you designed. So we are going to test it. After you test it, you are going to see how it would react based on what you want the PID to react. Like you want it to have like a certain level of overshoot. You accept that. It says and you see it has a higher overshoot that you want it to have. So what to do? We have to go back and play with that KD to get rid of that. Okay. We look at the output in the testing. We see, okay, there's still a residual error more than what we allowed the system to have. Let's go back and play with KI. The system would not react as fast as we want, or it would react too fast based on our design. Let's go back and correct KP. Very good. Then we fine tune, and this two-step is repeating until you get to the point that you want. And that's how you design the PID control. I added two videos. This one has an explanation, so that someone is explaining how to design the PID control. Okay, precisely in MATLAB. Okay, this one doesn't have any like speaking. No one speaks. It just show you how to like tune the values in MATLAB and like but this video gives you a very good kind of like a structure of how you could do that in MATLAB. Okay. Any question? You're good? Okay, if there is no question, that's it. So this is our discussion about the PID. Okay. Look for more information on the internet to know what the PID, how the PID works. I'm gonna add another kind of like practical point in power system, okay, because our frequency is strict, so our value is changing at 60 hertz. Okay, that means the speed of change in an error is basically already dictated by the frequency of the system. Can you follow that? So we are not gonna see a very high value of the change in our voltage, especially because in power system we have mostly inductive resistive load, which do not allow high change in the current, high change in the load. So we are not gonna see a very high rate of a change in our variable, ergo in our signals or error signals. What that means? That means practically, if we can't handle that, we could get rid of the derivative part because the speed is already defined. So it won't do much for us. Okay. It is better to have it, but if you want to go like a cheaper, simpler control system. In power system, you could get rid of the derivative part because you already know how fast you are changing. Are we good? So if you look at the video that I sent you for a hint before in the Canvas for this assignment, it's PI controller, not PID controller. That's the reason. Good. Any question? No? Thank you very much. So if there's no question, we could finish today's lecture. Have a great rest of the day.